So another important area for induction motor is, I think, also related to the air gap. I want to make clear that how the air gap will affect the whole magnetic design. So that will be important whenever we design inductor, transformer, and also induction motor. So firstly, to ask you, what do you think how the air gap affect the performance of the motor? Anybody can tell me something about that? Will the air gap, you prefer larger air gap or less air gap? What do you think about the difference between them? Smaller bit, why is that? Space. True, when we have a less air gap, so of course the magnetic field can penetrate much better. Then the magnetic field will be much stronger, larger, efficiency will be much better. But however, when the air gap is too small, we worry about the alignment. If the motor is not aligned properly, it may touch between the stator and rotor. If the air gap is really small, talking about a portion of a millimeter, we need to be really small. So that means the mechanical design is not easy, especially for tiny motor, very small motor, of course we can't afford to have large air gap. So that's why air gap design always with something, a compromise between the safety and also magnetic field. And then also relate to power factor. I think you did learn about power factor, right? Have you learned about power factor? Yeah. Yeah. We also have power factor in the motor. Yeah. When you energize some voltage into the AC motor, then we also measure voltage and current. The phase angle between them is the power factor. We do prefer have a high power factor because do you know why we prefer have high power factor?
Power factor means that voltages and current are the same, which means that we're circulating less current for the amount of work we're doing.
Yeah, good point. We don't like more circulating current. And then one thing you can see the power equal to V I and then cosine phi. So if the power factor of this one is small, right? For same power factor, the current must be larger. The same voltage. Voltage will not change, always 120 anyway. So when we have a system, lower voltage, low power factor, your current must be higher. You can see that for same kind of power rating, why we like to have high current means more conduction losses. You don't want that. So that means for all the motor, we prefer has much less current as possible. High power factor will be best. So less current pass through the copper winding, less power losses, less conduction losses. You see, when we did the solar farm, you can calculate the high current in the conductor have a huge losses, which we don't like. So power factor is something we need to be careful.
Question, how does the motor do power factor though? Don't you need like capacitors and like?
The motor is a winding. How about the winding? Capacitor power factor, inductor also have power factor issue.
Okay, so just using the.
One is a leading, one is a lagging, right? Yeah, both of them. If resistor, we don't have any power factor. But for induction motor, power factor, this is power factor. Power factor doesn't have any sign, only as a marker. But however, for engineer, we always think about power factor, like a leading power factor or lagging power factor. So that means for capacitor, the current is now leading the voltage. For inductor, it's lagging. So that means we also have this kind of leading or lagging power factor. Although simply for cosine below, cannot be any, right? So that's fine. But you do bear in mind, as an electrical engineer, we always think about that. But anyway, we prefer a high power factor. We try to decide how to make a power factor become higher for motor. That would be more beneficial anyway. And then we like to see what kind of air gap we like to do. The typical air gap, we know typical air gap will be, say, 1 millimeter, sometimes will be 1 point something, sometimes 0 point something. Roughly about that. For really huge motor must be larger for the safety. And then because of this one, we do have magnetizing current inside the motor. Magnetizing current, just like a transformer, we have the magnetizing, the LM, which is the magnetizing inductor. And the induction motor also really similar to a transformer. So after this chapter, we'll go through the equivalent circuitry for induction motor. Then you can see how they really look like a transformer. So that's why for all the machine courses, we usually teach you about transformer, so that from there you can use the principle of the equivalent circuitry for transformer apply in the motor. So we also like to understand more about magnetizing current, which more look like transformer magnetizing current. So this chapter, we go for a few things like the conventionally how we see the toroidal inductor, how the air gap become important, right? And then how the rotor structure look like. And then we go for a few tutorial for the induction motor air gap, how the air gap affect the performance, and then we make conclusion. So firstly, we see that air gap and rotor are so important consideration. We have the rotor rotating, and air gap will affect the efficiency, the safety, and also power level. So small air gap, we must have high power because we can able to create higher B field anyway. So that means we need to understand how to design air gap, what is phenomenon, large or small air gap, what happened. So what we first to do to see how the conventional design was toroidal inductor. So that's example I revisit from the transformer notes, look to page 14 to 15. During that time, we have a transformer core, 250 turn, and then the diameter side will 20 and 25, here 20, outside 25. Air gap will be 1 mm. And then we try to see if the mu out, we can from the BH curve in here, use the BH curve will be being used for design. And then we say here a particle 2.5 M. Then during that time we ask about the B field, the inductance, and the permeability at 2.5. So that's the thing we did. So let's see how we did that during that time. So we say the F phase radius will be 22.5, and then the H field will be equal to Ni, the MMF, divided by the length, 2 pi. This is the F phase radius, then we get the H field. That's a straightforward, simple equation. Right? And then according to BH field, if we got 442 here, 442 here, they got roughly about 1.2 something, right? So that's why from this point, we got B field with 1.225. And then in here, we can say the area, this little area, will be equal to 20 minus 25 divided by 2. And then get the radius, and then you get the air cross-section area, and the B field multiply area give it the flux. So that's why you can be able to get the flux to be 2.4. And then we like to calculate the inductance of the system. Then the number of turns multiplied by the flux, and then we divide by the current, we get us the 240. That is the inductance for that system. And then permeability for this, we can using this point say 1.22 in here, divide by the H 400 something. So the mu will be 0.0027. And then we try to remove the mu naught from here, we get the relative permeability. So that's how we did during that time. So that's a simplified method, how we're able to calculate under that coil system in metal core, and how we calculate inductance, the B field, the mu out. And then in this example, although we have air gap of those here, 1 mm, but we did not use the air gap here. So we are thinking air gap may not affect too much about the performance. So during that time, we only calculate it using the iron core to do that. So let's see what happens if we also include the air gap in the calculation. How it will affect the B field for the coil, because air gap affect the coil, also affect the induction motor. Let's see the phenomenon, what happened in that. So when we have air gap being considered, you add the MMF will therefore have a two component. One will be related to the H field contribution from the magnetic core. One will be contribution from the air gap. Just now from previous calculation, we try to ignore this one. You think, oh, air gap so small, I don't bother about it. But if we really include that in the calculation, what will happen? So 250 times 2.5 is the input MMF, and then we don't know the H field, how much. Then the length will be the circumference, right? 2 pi r, and plus air gap is 1 mm. We also H field in here. So that's how the equation should be. But just now we ignore this part. So because we don't know how much the mu out, then usually mu out can be given by the question or given by the manufacturer, or we can look up from the data book for the pH curve. Now in here, we got the curve here, then we can see. But because we don't know anything, we don't know what is H, we don't know which one to use. So we can just try to see a few. So you can see, take a few points from here to see how the mu out shall be. Because you can see the mu out in this point, and that point should be quite different. The curves are moving, right? So in here, we can say, if the B is 1.2, then about 400, we got the mu permeability becomes 0.03. And then the mu out becomes 2,000 something. Next, if we think when the H is large at 200 here, if we use 200, then the B field roughly about close to 0.98, then we got, that is the mu. And then the mu out will be nearly 3,800. And then besides, if the H field is small, say 100 in here, then the B field will be 0.69. Again, we can get the permeability will be 0.069. And then we divide the mu naught, will give us the relative permeability. So you can see that the curve, all along the curve, the mu out, the relative permeability vary with the material. So that usually gives us quite a problem. From 2,000 something, 3,000 something to 5,000, when you approach to more region, the mu are getting sharper, higher. That's reasonable because the curve will be this kind of curvature. So we don't know which one to use for the calculation. The best thing you can say, assume something first. We are assuming if you do an air gap, then probably the air gap will reduce the magnetic flux, reduce the B field. So probably we can use these two range because these look like lower H field or lower B field. So if we start by assuming the B around here, so that means the equation, you can be written by that. So that's our MMF. So that's a flux divided by the area mu naught. So that's actually our B here. Since we don't know the mu out here, we can assume roughly about taking average between the lower bound of these two. It may not be accurate, but you just give us some assumption first. So you use 4,000 something for the calculation, and then we put 4,000 something into this equation to calculate. So this air gap, we don't have any mu out usually 1 for air gap, and then for the core, then the mu out we assume become 4,000 something. We put into this equation. Now we got single unknown become B. We can calculate B becomes 0.6. So that's to say, if we consider air gap, then the B will now drop to 0.6. So quite a bit. Before was something like 1.2, but now dropped to 0.6. So you can see that using air gap actually affected the performance so much here. So according to the curve here, 0.6, then roughly the H field will be around here. Then calculate H will be about 80. So that means you can see that, of course, the curvature can give you different people when they look at the table, look at the curve, they can have different B and H combination. So assume we can able to 0.6, we can get 80. So that means now then we can redo the calculation for the inductance. So the area again is the same kind of area, doesn't change. The B is now 0.6 multiplied by area, then we got the magnetic flux. Then the flux linkage number of turn times the flux, we get 0.95, and then divide by the current 2.5. Now the new inductance 118. So you can see that with the air gap, the inductance dropped to 118. Before that, last time when we calculate, the inductance is 240. So you can see putting the air gap, the whole inductance for the whole machine dropped by half, right? So you can see that how powerful the air gap is. So the use of air gap, mainly you can see that all the machines we have air gap. We can't have rotor and stator touch each other, impossible. There must be a gap. The gap we use here is not large, only 1 mm. So that's how you can see that with the air gap, the inductance, the B field, everything dropped by such amount by become 118. So that's something we quite like to tell you about the effect for the air gap. And then we can also recalculate the B field. Now then we can use the new B and H. We calculate the mu becomes 6,000. We can transfer our field loop, put in the new mu out. We do the calculation again after our field loop. We can therefore calculate more exactly about the inductance. The thing is, we don't know exactly the mu out. We can only using trial and error to calculate our field time because the curve is moving. We don't have fixed value of mu out. So that's one of the way we can calculate the kind of the inductance. Then we do the calculation by using another material. For instance, in this curve, we got a few material. We have this material. If we're using this material, second curve here, again, we do the calculation to see what happened. Then we can the same kind of equation in here. And we assume that we can starting with the estimation start from 0.44, then H will be 329, which is something in here, 0.44, and so we got about this point for H field, right? So for this curve, you can able to get the permeability 0.0133. And then we can get our field point in here because the curve is also a so-called moving curve, a variating. It's not a linear, a fixed line. So we can get a field point now. Next, we got 700 in here. Then we can get the B equal 1. Then we get another permeability, another relative permeability 1,001 something. And then we try another lower one, 185. Then we got the B field 185, we got another one. So usually when we have air gap, then we tend to use a lower region of the curve because the B field usually will be lower. Then again, we use the same equation, and then we use the lower region of the prediction of mu r 962. We do the calculation again, then the B field will be 0.3, and then the associated H field will be 275. Then we can therefore we do the whole calculation, then L will be 62 mH. So what we're trying to see here will be this curve, we got a few hundred million mH for the inductor. When the curve is much less sharp, because you can see the mu out here will be much lower, then the permeability will be lower, and also the inductance will become lower. So you can see how this free curve, they tell you this curve usually higher inductance, lower and also lower. Once we insert air gap, everything will be changed. So finally, we do a comparison between for the first material we use. Before that, we don't use air gap to calculate. We can get the inductance 240. And the B field will 1.2, H field will be 442. Once we include air gap calculation, then you can see that the inductance will become 118. Yeah. The mu r, although it should not be changed, but however, it depends on which part of the curve we're trying to see. So it's very difficult to understand the mu because the curve is now moving. So, but the curve, you can see that near the bottom will be really high permeability. Near the top, more localized saturation will be much smaller. The material itself does not change, but the curvature of the curve will change. But key thing, you can see that in here, the inductance using air gap will drop in quite a lot. So you can see that this example is show you before when we don't consider the air gap, then the inductance, the B for everything will be quite high, which we like a motor to be high load, right? Even the inductor. But actually, for practice, we must have air gap. So in this case, we need to think about with air gap, how the inductance being changed was much lower. Even though for the inductor coil, stator coil, motor coil, then all the reluctance will be changed. So the key point we like to communicate with you. Any question up to this point? There's something flat to tell you what is the impression for the air gap phenomenon. So now then we understand more about air gap. Let's see what kind of air gap should happen in the motor system. So typically the air gap for motor will be usually tend to be quite small. 0.25 to 0.75 for small motor. So that's why I can say 1 mm only a little bit. So 0.25 is really small. For large motor, even a large motor, we don't make it really large, about 1 to 2 mm. So this kind of the size is really a key component to affect the overall efficiency, power, and force. You can see that when air gap is large, then your bearing, your alignment, you don't need to care too much. But once you want to have a small air gap, everything need to be really careful, this design. Like the bearing, alignment, everything will be quite complicated. But that affect the overall performance. So you can see that from the stator to motor design thing. So the magnetic core actually form a loop. The air gap actually, look how they flow. We firstly have the stator core, and then through the air gap, the magnetic field penetrate through the stator core, penetrate through the air gap, and go to the rotor core, and return to the air gap, and return to the stator core. It forms a loop. So that means you can see that the air gap have all the flux generate from here. You go through another portion, return, have a loop like doing that. So that is to say, if you see we got a stator in here, you got the rotor in here, you got some winding in here, you got some winding here. So the field generated in here penetrate. You don't need to go to the opposite side. They see a lowest reluctant path. Probably you can go back in this path to adjacent coil. It all depends on design, depends on how many pole, how the flux will go through. So, but the thing is, we don't like the air will be a much higher reluctant. So that's why the key thing is all these things, the mu out will be much, much higher. But the mu out for the air usually will be equal to 1. We don't like that. The mu out for this will be a few thousand. Actually, you can see just now. So that is why you can see that the air gap will be a dominant item to design everything. So we can see here that another item we want to introduce to you with the magnetizing current, which just really look like the transformer magnetizing current through the magnetic core, which also appear in this stator to rotor design. The stator look like primary, rotor look like the secondary side. Between them, we have the magnetizing, which we always some magnetizing current go through the magnetic core. So later on, perhaps in next looks, we can see that we also will model the transformer like this. So this side will be our stator. This side will be our rotor. So this side will also have the motor within R1, maybe some X1, R2, X2, and then also have a magnetizing component, which you can see that when our motor is stationary, it just looks like a transformer. So that's why you can able to still see that magnetized current going through the magnetizing inductor. It look like how the current being flow through them anyway. So we already passed through 15. Any question up to this point? We continue to discuss that about the air gap. It's very interesting, but could be very boring to you, but something important we must go through that. Anyway,